So, sorry for the delayed start. Welcome to the Open Tools for Open Science Reproducibility workshop. So this is this month's installment, and specifically going to be looking at the programming language R. So my name is Conor Goold. I'm a visiting researcher at the moment in the School of Biology. I was a postdoctoral research fellow up until the end of last year. And I currently work also as a data scientist just for a private company. So I'm hoping that I can give a kind of broad overview of the usefulness of R for reproducible research. And obviously with this amount of time, we don't have time to have a full-on practical session using R. And I've attended a number of workshops that have tried to do too much before with something like R or programming. So I've tried to focus on just a few main areas to give hopefully the most of you some ideas about how you can use R in a reproducible fashion. So both brand new beginner people to R, but also those of you who might have a bit of experience using R and what you can do to advance yourselves. So first, we're going to look at some motivation for why this is important. So you might have seen this graph before from a 2016 survey in Nature of, I think, around 1,500 different scientists, where they're looking at what drives irreproducible research. So at the top, we have things like selective reporting and pressure to publish, which we might expect, but we've also got topics related to data analysis, so things like low statistical power or poor analysis, methods in code unavailable, raw data not available from the original lab. And when the same people were asked about what factors could actually improve reproducibility, then the top one was better understanding of statistics. And incentives for better practice is in general something that comes up with improving reproducibility, and practical data analysis skills. If we give people the incentives for using them and learning R and making these things accessible, then hopefully that will encourage other people to use them. And this is just one example that we could look at in terms of how statistical errors come into the reproducibility crisis. This is a paper looking at, I think, around 250,000 different p-values in a bunch of different psychology journals from 1985 to 2015. And the top panel shows the total percentage of papers that had an inconsistency in the white bars, or a gross inconsistency in the gray bars. So an inconsistency was a case where the p-value didn't match some of the statistics in the article. So there's a mismatch between the test statistics in the article and the p-value being reported. And then the gray gross inconsistency is where those inconsistencies would have caused if not reported wrongly, a completely different conclusion of the study. So you can see around 60% in some cases of articles had an inconsistency, and around between kind of 5 and 15% of articles had a gross inconsistency in their results. And down here is the within article percentage, average percentage of inconsistencies and gross inconsistencies. And importantly, the authors used an R package to do this analysis. So they used an R package called StatCheck, which was able to test all the statistics from raw PDF files of articles. And this just goes to show that these statistical errors are not necessarily from fraud or bad practices that are conscious, but they come from unconscious processes. It's often mistakes or poor understanding of what people are doing in data analysis. And so computational reproducibility, the ability to recreate study results, is at the heart of the reproducibility crisis. And sometimes we have a separate name for this, which is called computational reproducibility, but actually it really gets at the heart of the reproducibility movement in general. So the National Academy of Science, Engineers and Engineering and Medicine in 2019 said that reproducibility is obtaining consistent results using the same input data, computational steps, methods, and code, and conditions of analysis. And that this definition is synonymous with computational reproducibility. The problem is that modern data analysis methods do require some literacy in programming. But after that kind of small learning curve, you can greatly support your reproducible practices by using more modern methods like those in the computer language R. So for those of you who have never used R before, or maybe any other type of computer programming language, then it's worth using or learning how to use it purely from the basis of it will allow the whole reproducibility workflow to more easily instantiate that workflow. So we asked you to look at this paper, Publisher Code, It Is Good Enough, by Nick Barnes, who's a software engineer, just before the session. It was a very short opinion piece where it was argued that you don't need to be worried if your computer coding skills aren't very good, or the code is a bit messy, or you're just a beginner. It is good enough to share, and that's largely because the alternative, not sharing your code, is even worse. It's much less reproducible. Even the messiest code can be more reproducible than running your analyses in say a point and click based software where we don't know what the steps that were undertaken to do the analysis. And in reality, most people's codes are like that. So even in professional settings, code bases can be messy, and they can lack documentation, or they can lack finesse, for want of a better word. So it's always good. We'd encourage you just to dive into something like R, computer coding, and give it your best shot, and don't worry about not being good enough, or things not looking as good as they could be. So with that introduction, the different topics I'm going to cover, we'll go quite slowly at first. We're going to look at what R is in general and how do you use it, where do you download it from, how would you run it. The second topic we're going to look at is writing scripts for reproducible documentation. So a script is just a list of commands. That's all it is. But that list of commands is really powerful in a reproducible science setting, because it gives a direct window into the steps that we've taken to do an analysis, which we can't really get from if we just had a computer program that was point and click software. Or we could give a big list of point and click routines, but it would be very difficult to document. We're then within this going to look at the topic of functions and how to break your code into functions and the importance of that. And also looking at directory structures, because it's very hard to reproduce someone's results if you have a bunch of different files in a very difficult order. And that gets at the heart of this, of using R for reproducible research. And lastly, we're going to look at beyond the basics of R programming and look at packages in R and a couple of techniques for fostering reproducibility. So I've got some example packages here that I'm going to briefly mention, some topics about reporting and presenting results and how you can do that in a reproducible way. And then we're going to end with looking at a technique that I think is very useful for both beginners and more advanced users, if they don't know it already, to use in their research, and R can directly facilitate that. Okay, so what is R? If you've never used it before, if you don't know anything about it, well, it's a statistical computing language and environment. So it comes from a programming language called S, would you believe it? And R is essentially S just wrapped up into kind of a nicer environment, and it can be run in different formats. So the simplest way is base R. And that's, if you go to this website here, which is shown here, you'll see on the left-hand side, it's got a download section, and you can download R onto your computer, and you get a very basic window which you can type in commands and use R functionality. You can run R in the terminal or the command prompt on your computer as well, but I'm going to assume that most people don't know how to, or are not that familiar with the command line. So this is really the easiest way, the simplest way. The easiest way, which isn't necessarily the simplest way, is to use base R and what's called RStudio, which is an integrated development environment, and it provides a kind of fancier interface essentially with R. So you don't get just a simple window. You get a window with different panes, and you can plot results more easily. You can look at data more easily. So that's at this website here. I'm not going to go in at the moment, at least, not going to go into R and show you directly into R. Just from the interest of time. If we've got time left over and you want to do that, I'm happy to do that. I do have code examples throughout the presentation on the slides that you can use and you can plug into R yourselves. So a good way of thinking about R at the start is that it's just a big calculator. So it contains a number of different routines to do different computations. So you can do 2 + 2, and you can get out 4. So in these yellow code boxes, when you see these, the double arrows here, that's the output of R. That's essentially what you would get if you plug this into R. And R is an object-oriented programming language, which essentially means that it's built around objects where we can put values into those objects, and those objects can be manipulated later. So in this example, we've got X, which we assign using this operator, which is very bespoke to R. Sometimes you'll see computer languages or just use the equal sign, but R uses this. So here we're saying that we're assigning the value of 2 to X. And similarly, we can assign the value of 2 to Y if we want. And now the real power of this is that you can say X plus Y, and you also get 4, the same way that we did 2 + 2 is equal to 4 here. So X and Y actually hold the values of 2. We can then override a value really easily by just running the same command but changing what the value that we're assigning to X to. So we can say that X is now equal to 3, and we can say X plus Y, and now we get 5. So this is really a simple example of object-oriented programming, but this is where the power of R is. You can imagine that if you have a number of more complicated objects like data, data sheets like coming from Excel, you can start to manipulate the data and create new objects pretty easily, and essentially create a full analysis pipeline from this kind of simple topic or simple concept. So if you have started out in R and you start plugging these types of things into the console, that's all well and good, but eventually you're going to start wanting to remember what you were doing before. And for that purpose, scripts really are your friend. So a script is a plain text file, and it contains all the computer code used to run the procedures of collecting and cleaning and organizing the data, and eventually analyzing and plotting your data. So this is a simple example of what a script file might look like. We use the .r extension rather than the .txt extension. And in some editors, it will show you some nice syntax highlighting for the R language. In R, the hash symbols are just comments. So we can comment our code and write anything that we want to do with the description of the code that we're going to write. This is really considered a best practice in all programming languages. It's always useful to say what you're going to do and what different commands do. So in this example, we have an analysis.r file. You've got some description. This is my analysis script. We might want to load some data in. So here we're going to assign to the variable d some data, and this data is actually coming from a CSV file. And R's got a built-in command here called read.csv, and so we can hold that data now in a variable d. We might want to then clean some data, so we create a new variable, dclean. Importantly, variable names can't have any spaces in them, they can't start with numbers, and they can't have any dashes in them. So you'll see that I often use these underscores to kind of make it clear what it is. You don't need an underscore, but I just think it's easier to split it up this way. We might want to create this dclean variable, and I haven't put any code in here for this example, but you could write some code that, for example, just removes some columns. And then we might want to transform the data for analysis. So we create a new variable called dAnalysisReady, and then we do something, we transform it in some way. We have transformed the dclean data set. So if you just think about having this in a script and versus a point-and-click based software, it'd be really hard to express this pattern of activity in, for instance, if you were using Excel or using Stata or using SAS or Minitab or anything like that, or SPSS. So these simple scripts hold the key to reproducible analysis. You can share these scripts with colleagues, you can share them on public repositories, they can be read easily, they don't require any particular software to understand them. You can open them in simple text editors and notepads or whatever you have. So I would advise anyone who's starting out with R, jump straight into writing some scripts. After you've kind of figured out what the console looks like, you can start to write up your own scripts and just have that. And the idea is that you would copy these commands into the R console and run it, which if we have some time later on, I can show you exactly. RStudio has a few more different pieces of functionality to allow you to just run some select lines much easier. So the next stage to look at is functions, which are really the core of computer programming. And a function is just a wrapper, essentially. So it wraps procedures for later use. So we might, in R, the way we define a function is we give the function a name called myFunction. We use the assignment operator again. Then we use the built-in word function. And function then takes a number of arguments. We might have a number of inputs to that function, and between some curly braces, we give the different procedures that we want to do to the input. So for instance, if we just want to multiply something by 2, we can define a new variable called output, and it's going to be the input times 2, and then this returns the output. So importantly, this is not running anything yet. All this does is it tells R, it defines this function in R, so that later on we can use it. The input is just a copy of whatever we give it. So if we give it a variable, if we give myFunction a variable in R, then it just copies that, uses it in this function, and spits out the results. It doesn't actually change outside of the function, the input variable. So to give you an example, we start off again with x is equal to 2, and we have our function definition. We can say that myFunction, we can give it the input is equal to x. This then grabs x and it creates a copy of it, and it runs all of this in between the curly braces. So here we know that the output is going to be x times 2. And the return point is going to be just spits out this output. So here, that's what happens. We give it x, which is equal to 2, and it spits out 4, which is just x times 2. Importantly, if we look at x and just print out x alone, it hasn't changed from up here. So that might seem a bit confusing at first, but it's because this function is just creating a copy. It's not actually changing this original variable, and that's a good thing because that would be quite dangerous if it did do that. So x is still equal to 2 outside, but the return result of my function is 4. So where this is going is that it's really important and really useful that you can break up your code routines into functions. So imagine that you have a big long script of all your data analysis, and it's easily a couple of hundred lines long, and you then go and try and share it to someone, and it causes no amount of headaches trying to understand what the code does. So what we can do is we can split up our code into different files, and we can define different functions, and then we can use those functions in some other scripts. So imagine that you have a myfunctions.r file. But could everyone just check if they're muted? I think there's some. Oh, sorry, everyone. Yeah, I think there's someone's microphone's on, and we can hear you pressing your keyboard. So the myfunctions.r file can include a couple of different functions. So here we've got a function for adding two numbers together. So just as before, we can give it a name. It can be any name we want. We say it's a function and it takes two variables, x and y. You can choose whatever names that you want for these. I've just chosen x and y. And here we're going to return x plus y. So that's going to return that this function is going to return the sum of two variables, x and y. We might have another function which is a bit more real world case called clean data, and this is going to take some data, and we might want to do some operations to it, such as use our function up here. We might want to add two variables together and return that clean data for later use. So it doesn't matter exactly what's in here. It just matters that you have a different file with some functions in it. We can then use what's called the source function in R to access those functions. So let's imagine we have another file called analysis.r, and we want to use our functions and to some data. So R needs to know where our functions are kept. So we can use the set working directory function and give it the file path. So we might have a folder on our computer called my project, and we're going to tell R every time we tell it to look for a file, it's going to be in this folder. We can use what's called the source function, as I said before, and we can give it the myfunctions.r file. And this then just runs everything that was in the previous file. So it makes it accessible in our current, in the console. So then we might want to read some data like we did before. So we get our data, and we then want to apply our function to the data. So we want to apply this function, clean data, to our function, and then now our R has access to it. So this is much shorter. This script is much shorter, analysis.r, than it would be if you had to have all of these defined and run all this later on. It would get quite messy. So here, by using the source function, we can just access the files that we have. So this leads us to having clean and readable directory structures. So I like to have a project folder, and I like to keep my code all in a single file. And it's useful to split it up into different intelligible sections. So I usually have a functions.r file. I might have a cleaning.r file, so this actually cleans the data. And we might have analysis.r file. And then we might have some other parts of the subfolders, maybe one for keeping the paper itself, and then one keeping the data. And in this way, and using R and using the source function, we can make a reproducible and easily understandable directory structure. And with tools such as version control, which don't really have time to go through it in detail, but version control tools like Git is very common and very easy to use. It allows us to keep the same file names, and version control systems like Git will keep track of all the changes that are happening in those files without having to change the file names themselves at all. You can always go back and see what changes you've made, and you don't need to create like a final functions version 1000 or a cleaning final data set. So that's the key of reproducible packaging of your data and your code comes from having a clear and easy working directory structure. Okay, so let's go beyond the simple R programming here and look at some of the capabilities that R has in terms of its packages that you can download from the internet that foster reproducibility. So this is maybe going to people who are a bit more intermediate in R, and hopefully give some of you people who are beginners in R where to look first. So R is an open source community. It's completely free, and it depends on other people building software and building different packages, which are just collections of functions, and uploading them to what's known as CRAN, the Comprehensive R Archive Network, and makes data analysis easier. So if you have a function which you think is really useful and would be really useful in a general context to people in your field, then you can create that function and you can package it up and give it to CRAN. And then other people can download and use it. So these are some of the top downloaded packages in R at the moment. If you know a little bit of R, you might recognize some of them. DPLYR is a data manipulation tools package. RCPP is a package that allows you to integrate C++ code into R. C++ code is much quicker to run, so you can actually interface R with all different types of other programming languages using different packages. ggplot2 is a famous and very elegant plotting package for graphics. So I want to go through 3 different packages that I think would be useful for everyone to have some awareness of when they're approaching R, and if you're doing some analyses in R. The first one is PackRat, which is a dependency management system. So you can imagine that because it's an open source product, or open source software, people are updating packages and updating R constantly. So there might be small changes entering, and we need to keep track then of the different versions that are that we're using for our analyses, because if a package changes between the time that you did the analysis and someone else did the analysis, then that could create problems for reproducibility. So you can go here to this rstudio.github link to look at what PackRat is, but PackRat essentially keeps track of all the different versions that you have and you're using on your computer at the time you do the analysis. So I've got just a quick example script of how you would use it. R has an install.packages script, and you can download a PackRat by using this line of code here. You just include the name of the package that you want in inverted commas. And then when you have PackRat, you can basically tell it to initialize itself in a different repository. So you might have a my project repository or folder on your computer, and you want to initialize PackRat in it. So then that tracks everything that's going on in your folder to do with R. You might want to then download another package called install.packages, and it could be the RCPP package. And then you use a function called snapshot in PackRat, and then the output of that shows you what version you've got for RCPP. So you can have a look at the different examples that are on the website for this one. A piece of our programming here just to look at is I use these double commas. So when you download different packages, you can either use these double commas to access to access the functions within those packages. So I'm saying in the PackRat package, access the function in it, or in the PackRat package, access the function snapshot. You can also load in the library directly by either using the library function or the require function in R, and that means that you just don't need to write this part first. You can use this part second. But sometimes when you're learning, it's a bit easier to see what functions come from which packages when you use this double colon. So the PackRat package is essential for understanding how analyses, or what versions different analyses were run under. The second package to look at is the Drake package. So this is, as you'll see here, this is from its GitHub page, which is an open source website for keeping all the packages. It helps you have a reproducible workflow of data analysis. So as it says here, it skips steps with up-to-date results, and it orchestrates all the data analysis, optionally on distributed computing systems. And I've got another quick example here to make it kind of more obvious. It comes with a function called Drake plan, and it allows you to define what the procedures that you want to do to do your analyses. So I might want to create a new analysis plan called my analysis plan. I might want to read some data in like we did before. I might want to clean some data and get some clean data out of it. I then might want to run a t-test on the data. So I can take the results of the t-test. R's got a built-in function called t.test, and I might want to run it on some aspects of the clean data. You can then, for example, plot some data, and on and on and on. If I run this, and then I can use the Drake's make function, Drake will run all these different steps in order and will save the results for us. It saves the results outside of R in a separate file. And if I wanted to come back to this analysis and do the analysis again, it will only run the sections of results that are different. It then gives you a reproducible, what's called data analysis pipeline, and you can much more easily read this if you come into someone else's code to understand what was done. You can see that they've just read in some data, they've done some cleaning on the data, they've ran the result analyses, and they've created a plot. And so hopefully these types of packages are going to be becoming much more a mainstay. And lastly, the testthat package is used for what's called unit testing. So for this, you have to think a bit like a software engineer, where you have some code, and unit testing is just testing if that code works, usually by giving some code, a really simple example that you know what the output should be, and you just want to check if the code gives you the desired output. So this is the testthat overview page that you can look at on GitHub, or just typing in testthat into Google. It tells you that testing your code can be painful and tedious, but this package aims to make that much more easy. So I've got another quick example here. We can access the testthat functionality by using the testthat keyword and the double colons. Testthat have a number of different expect functions, so you can tell it what you expect it to happen. So I use what's their expect equal function here, and then within that I give it some something that one of my functions, in this case the clean data function, and let's say the clean data function is meant to remove these NA values. NA just is usually a missing value in R. So I've given, I'm kind of ramping up the complexity of the code here for some of you in terms if it's helpful to look at, or for those of you that have seen this type of code before. It's here we're just creating a new vector of values, 1, NA, and 3. This is like a little list of values, and I'm applying clean data to this. And clean data should remove the NA. And so I'm using the length function here. So the output of this should actually be 2, because the clean data function should remove the NA value, and then the length of that vector is now just 1 and 3. So the total length of the vector should be 2. And so I tell expect equal that the expected output should be 2 of this. And it will throw an error if that's not true. So what this means is that I can give it a number of different example cases, all of my different functions that I've defined, and the different functionality that I need in my analysis plan, and I can test if the code is actually working correctly. So this is very much a software engineering principle that doesn't often come into academia as much, but it's something that I think people are thinking about much more nowadays, and understanding that we need to do this if we want our code to be reproducible. So I'd really recommend you look at this lecture if you're interested in this topic by Richard McElreath, who's a researcher in Leipzig at the Max Planck Institute. He's an evolutionary ecologist, and he is a big proponent of software development principles to try and save science, if you like, so make science more reproducible. So it's about nearly an hour-long lecture, but it's very useful for anyone who is new to this topic. Okay, so we're now going to look at some things to do with writing and presenting research in R, using R code. So R is, or has in the last number of years, really grown into an integrated environment for presenting results in different formats. You can create websites, you can create PDF documents, HTML documents, you can create slides, you can create Word documents from R. And a lot of this is down to what's called the R Markdown system, or R Markdown format. So this is a picture of RStudio, and you can define different files like an R Markdown file. And what this file does is it integrates a written text. So here we've just got some written text, and it integrates that with R code. So you can see that it's defined by these different blocks of R code. You can write the R code directly in there, and it will put the output of the R code into the document for you. You can then compile this into whatever format that you want. If you want it as a PDF, or you want it as a Word document, or you want it as HTML, you can do that. So this is just an example here of what it would look like. You can put it on your website, you can put it on a blog, and you can see that the code is nicely formatted. You have options of, you don't need to show the code at all. You don't need to show any plots if you don't want to. You can just have the code running in the background and maybe create a table for the results, whatever you would like. So I know people write their whole research articles in this format now as well. So they actually write the introduction of their paper, they write the methods up, and then in the results, or in the analysis and results section, they actually have the R code hidden, and that's how they do write their scientific publications. And so that stops people from keeping their analyses separate from the paper writing and creating tables, or maybe copying values from R into a table, which can introduce errors. And the other thing to look at in terms of the R universe is Shiny apps. So you might have seen these apps before. Shiny apps are a simple way of creating and hosting different applications which can show you results, or maybe create a report, or if you're into computational science, then you might have a model that you want to show people. And you can create a simple interface for people to go to at a URL link, and they can access that application. So this is a Google Trend Index application. This is what it would look like in the website, and this is some of the code underneath it. You've got options for creating drop-down boxes. You can load data in. You can plot different visualizations. You can have tables. You can save data from these applications. And the core of it is just simple R code. You usually write some functions and some code for the analysis that you want to do, and then you have another section of the code that tells R what the app's going to look like, and then R does the rest for you. And Shiny will the Shiny functionality will create a nice looking application. So if people are doing a PhD project and they want to have some more outreach for their science, and R Shiny application is a great option. Also the same for articles. If you have an article and you want to show some results, then having an R Shiny application is actually really useful. So before we finish, I just want to end with a topic that is very close to R's functionality, but is also related to the reproducibility movement, and kind of gives some impetus for learning something like R. So fake data simulation is it's not fabricating data for any bad purpose. It's simply simulating data, dummy data, in your computer, which you can use to test your analysis before analyzing your data, before collecting your data if you want. R has rich functionality to simulate different types of data for you. And so this is an example blog website by a famous statistician called Andrew Gelman, and he's written quite a bit about the usefulness of fake data simulation as a research tool. He's a big proponent of open science. So I encourage you to maybe look at this blog at the start. But fake data simulation can help you in a number of ways. It can help you check your understanding of the statistics, so you can actually understand what your future analysis will actually look like, and what the results format will look like. And if you understand how that works, you can conduct power analyses more flexibly this way. You can have a routine in R where you do your power analysis and report that maybe in a grant report or whatever it might be. You can add these routines to pre-registration documents. So before you've collected any data, you can show people exactly what your analysis plan is going to be and how that looks, and you can make sure that your code actually works and there's no bugs in your code. and you can create your whole analysis pipeline before conducting your study. So I want to give a small example where I've got some equations in here. It's just a simple example of a linear regression. If you don't know what a linear regression is, don't worry, it's just fitting a straight line to some data. But I wanted to just give a brief example to show you how R simulates data and some of the different functions. So we might start from some theoretical principle. Let's say we do a study. We know we're going to collect some data. That's going to be Y is going to be the data that we've collected in our study. And then we want to analyze maybe how Y is impacted by some predictor variables. Let's say we're looking at intelligence tests or something like that in psychology. We've got a bunch of different results from people, and maybe we want to collect the age of the person. And that could be our predictor variable in our analysis. And the whole point of our study is to look if age impacts intelligence. So we might want to use a linear regression for that purpose. So we say that Y has some distribution, and the mean of the distribution is given by this equation, which is equation for a straight line. So we have an intercept and the effect of the X variable on the mean of this distribution. So if you're not familiar with linear regression, I'm sorry for jumping straight into this. If you are, then hopefully that's interpretable. In R, we can simulate data to check how we do this analysis before running the study at all. So this is some example code. You can copy this directly into R. We might want to first say how many data points that we want. So let's say in our actual study, we're going to collect 100 different people's intelligence tests. We give R some dummy parameter values. So these different A and B are different parameter values, and the sigma is a different parameter value. So we actually tell R what we want the values to be. We create an X variable. So this is just some fake age data. So we can use the R norm function in R to create samples from a normal distribution. So R has got a number of different functions starting with R, which stands for basically random. So random normal, you can think about this function as, and it will get 100 different samples and assign that to X. We can then write out exactly our formula. And so where I'm going with this is that you can help understand statistics and learn statistics by this process. So here we've got this value mu, which is this Greek letter, and we can give it directly the formula for the linear regression. And then we can also say that we can generate the Y data by, again, using the normal distribution. So you can read this the same way that this top line is read. So Y is a normally distributed, and we want 100 data points, and we want a mean of mu and a standard deviation of sigma. So Y will hold some fake data now that we know has been generated by this process. And then in R, we can use the LM function, which is a linear model function for the linear regression. We can run that, and we can also summarize that. So this line of code will summarize the results. And you can look at the results, and R here will say that the intercept, which is our A value, we said it was 10. You can see it's very close to 10. And it has the effect, this is the effect of X, which is the B value, which we specify as 2. And you can see it's very close to 2. So I know now I can keep this code, or I can keep particularly this code, and I know that it's going to result in what I expect. So when I collect my study, before I've even done the study, when I collect my study data before I've even done the study, I know exactly what I'm going to run to get my analysis results. I don't need to spend ages trying to figure out what analysis I should be doing. After you've collected the data, everything can be good to go, and you can put something like this in a pre-registration document for people to view. Okay, so that's all I have for this presentation. I hope it's been probably a bit of a whirlwind for some of you of a whistle-stop tour of the different functionality in R. Some excellent resources that I just want to quickly recommend. There's a package called Swirl in R, which allows you to go through a few different tutorials directly in the R console. So all you need to do when you download R is use the install.packages swirl function, and then you run this. So you run the swirl function from the swirl package, and that will then enter a little tutorial for you. It'll ask you to do a few things, enter your name, and it'll run you through some different tasks in R. And it's really excellent for getting to understand the different functionality that R has. There's a free book, R for Data Science by Wickham and Grolemund, which is constantly being updated and is one of the most famous books out there. So I recommend that for more beginner to intermediate users. And then there's a bunch of different free courses on DataCamp that you can check out for some more information.